Swayam Prabha. Digital India. Educated India.
Welcome to lecture 35 of the course on econometric methods for statisticians, data scientists and data engineers. The title of this lecture is Two-Stage Least Squares and Limited Information Maximum Likelihood Estimators. Before estimating the parameters of a particular structural equation, we check the identifiability of that equation. Of course, if the equation is unidentified, then we cannot estimate the parameters of the equation. And if the equation is identified, then we go for the estimation. In the last lecture, we have discussed the indirect least squares procedure for estimating the parameters of a structural equation. Now, one can apply indirect least square estimation procedure if the equation is just identified. Suppose a particular structural equation is over identified, then what happens? If we solve the relationship between reduced form coefficients and structural parameters and try to find out the reduced structural parameters in terms of the reduced form coefficients, then we get more than one solutions. So, obviously, if we apply the indirect least square procedure, then we get more than one estimators. So, in such situations, the indirect least square procedure fails to provide a unique estimator, and then you require some alternative estimation procedure. One of the alternative estimation procedure is two-stage least squares estimator. Now, in this lecture, we are going to discuss the estimation procedure using the two-stage least square estimator. If the equation is over identified, then how to use the two-stage least squares procedure for estimating the structural parameters. And then we will also discuss the consistency properties of the two-stage least square estimator. And then we will move to the estimation of a parameters of a particular structural equation using the limited information maximum likelihood procedure. Suppose a particular equation is over identified, then it means you have more than enough information in the data to estimate the model parameters. And if you look at the relations between the structural and reduced form parameters, and if you solve these equations or these relations for the structural parameters, then it leads to more than one solutions for the structural parameters. And since you are getting more than one solution, so if you apply the indirect least square procedure, then you get more than one estimators. So, indirect least square estimator is not unique. So, it cannot be used. And since indirect least square estimator fails to provide you a unique estimator, we look for some alternative estimation procedure, and one of the alternative estimation procedure is two-stage least squares estimator. So, we consider the estimation of an over identified equation and the two-stage least square estimation procedure. So, first we explain the procedure with the help of an example. So, we have this system of equations. The system of equations has an income function I f, which is y 1 t equal to beta 1 naught plus beta 1 1 y 2 t plus gamma 1 1 x 1 t plus gamma 1 2 x 2 t plus u 1 t. And then it has a money supply function, which is y 2 t equal to beta 2 naught plus beta 2 1 y 1 t plus u 2 t. Here y 1 denotes the income, y 2 denotes the stock of money, and these two are the endogenous variables. So, we are denoting the endogenous variables y's. Then x 1 is investment expenditure and x 2 is government expenditure. These two are exogenous variables. Now, you can easily verify that the first equation I f is under identified, and money supply function, the second equation, is over identified. So, you cannot estimate the parameters of first equation, and since the second equation money supply function is over identified, you cannot apply the method of indirect least squares for estimating the parameters of money supply function, but we can apply the method of two stage least square for estimating the parameters of money supply function. And these are the steps for two stage least square procedure. So, the first step is regress y 1 on all the predetermined variables in the system. Now, notice that the second equation has one of the endogenous variables y 1 t on the right hand side as explanatory variable, and the problem arises because of the correlation between y 1 t and u 2 t. So, what we do? We take y 1 t, which is the set of all endogenous variables present in this particular equation except y 2, and then we regress y 1 on all the predetermined variables in the system. And here you have just two predetermined variables except the interceptor. Of course, you have the interceptor also. So, the two predetermined variables are x 1 and x 2. So, we run regression between y 1 and x 1 x 2. You simply run OLS between y 1 and x 1 x 2, and then you obtain the predicted value of y 1. So, first you obtain the least square estimators for pi naught, pi 1 and pi 2, and then the predicted value of y 1 is y 1 t hat equal to pi naught hat plus pi 1 hat x 1 t plus pi 2 hat x 2 t. Now, you can write the model as, or before that we write y 1 t as, say, y 1 t hat plus E t, where E t is the OLS residual. Actually, E t is equal to y 1 t minus y 1 t hat, or y 1 t minus pi naught hat minus pi 1 hat x 1 t minus pi 2 hat x 2 t. So, E t is the OLS residual. So, first we write y 1 t in this form, and then we write the second equation, the money supply function, as in step 2 we write money supply function as, say, y 2 t equal to beta 2 0 plus you replace y 1 t by y 1 t hat plus E t plus u 2 t, and then this is equal to beta 2 naught plus beta 2 1 y 1 t hat plus we take beta 21 E t with u 2 t. So, this is your combined error term or disturbance term. So, finally, we get the relation y 2 t equal to beta 2 naught plus beta 2 1 y 1 t hat plus u t star, where u t star is equal to beta 2 1 E t plus u 2 t. Now, y 1 t hat is uncorrelated with u t star equal to beta 2 1 E t plus u 2 t. How you get y 1 t hat? We run regression between y 1 t and x 1 t, x 2 t, and then we get this predicted value. So, it is uncorrelated with these residuals. This predicted value is uncorrelated with the OLS residual E t. Then this is also uncorrelated with u 2 t. It does not involve u 2 t. So, it is uncorrelated with u 2 t. So, in fact, y 1 t hat is uncorrelated with this combined disturbance term beta 2 1 E t plus u 2 t. Now, you can apply OLS to this equation, and then you get the two stage least square estimators for beta 2 0 and beta 2 1. So, again we look at the steps for two stage least square procedure. So, you have to estimate the second equation, this one. So, now you look at all the endogenous variables present in the second equation except this y 2. So, here you have just one endogenous variable y 1 t. Then you run regression between y 1 t and all the t determined variables, that is y 1 t and x 1 t, x 2 t. And then we find the predicted value of y 1 t. Then in the model, we replace y 1 t by y 1 t hat, its predicted value, and then we run the regression for obtaining the estimators for beta 2 0 and beta 2 1. So, this is how we get the two stage least square estimator. In the first stage, we are obtaining the predicted value of y 1. In the second stage, we are replacing y 1 by its predicted value, and then we are applying the least square procedure, and then we get the final estimator. So, now we consider the general form of two stage least squares or generalized classical linear method. Actually, the generalized least square estimator delta curve may also be interpreted as a two stage least square estimator. Now, suppose you have to estimate this equation, small y 1 equal to capital Y 1 beta plus x 1 gamma plus u 1. And we assume that capital K minus small k is greater than or equal to m minus 1. That is, the equation is either exactly identified or it is over identified. Then the two stage least square estimator of beta gamma can be obtained by solving the equation, say y 1 transpose y 1 minus v 1 transpose v 1. Here you have, then you have y 1 transpose x 1, then x 1 transpose y 1, x 1 transpose x 1, B c equal to y 1 minus v 1 transpose y small y 1, x 1 transpose small y 1. Here V 1 is equal to I n minus x, x transpose x inverse, x transpose y 1. So, or you can write it as y 1 minus y 1 head, where y 1 head is equal to x, x transpose x inverse, x transpose y 1. Obviously, if you take x transpose V 1, then x transpose I n minus x, x transpose x inverse x transpose, this is equal to 0. So, this shows that x transpose V 1 is equal to 0, and then this implies that x 1 transpose V 1 is 0, x 2 transpose V 1 is 0, because you can write x equal to x 1 x 2. So, x transpose this matrix means, so suppose you write this matrix as P, then x transpose P is equal to x 1 transpose P, x 2 transpose P. So, both are 0, and this implies that x 1 transpose V 1 is equal to 0, x 2 transpose V 1 is equal to 0. And then this implies that x 1 transpose y 1 head is equal to x 1 transpose y 1 minus V 1. You can write y 1 head equal to y 1 minus V 1 from here, and then second term is 0. So, you get x 1 transpose y 1 here. So, x 1 transpose y 1 head is equal to x 1 transpose y 1. So, now we derive this expression for the two stage least square estimator. So, suppose we write capital Y equal to small y 1, capital Y 1, capital Y 2, capital X equal to x 1, x 2. Here small y 1 is of order n cross 1, capital Y 1 is of order n cross m minus 1, capital Y 2 is of order n cross capital M minus small m. So, this capital Y 2 includes the endogenous variables which are not included in this particular equation. Your equation is y 1 equal to y 1 beta plus x 1 gamma plus say u. This is your equation, or you can write it as y 1 beta plus y 2 into 0 plus x 1 gamma plus x 2 into 0 plus u 1. So, y 2 is the matrix of observations on endogenous variables which are not included in this particular equation. Further, x 1 is of order n cross small k and x 2 is of order n cross capital K minus small k. Again, capital X 2 is the matrix of observations on the predetermined variables not included in this particular equation. So, we write capital Y and capital X in this form. Then reduced form is capital Y equal to x pi transpose plus V. Then we apply OLS to the reduced form, and then the predicted value of y is y head equal to x, x transpose x inverse x transpose y. And then suppose we take p equal to x, x transpose x inverse x transpose, then y head is equal to p y. So, y head is actually the predicted value of y when you run regression between capital Y and all the predetermined variables x's. Basically, what you are doing? You are running regression between all the endogenous variables and all the predetermined variables, and using this regression you are predicting the value of capital Y. So, y hat is equal to this. You can easily verify that this P is an idempotent matrix, and basically for employing two-stage least square procedure in this equation, you want to replace this capital Y 1 by its predicted value. So, you are interested in obtaining the predicted value of Y 1. So, from this equation we obtain Y 1 hat equal to P Y 1. So, just take the corresponding elements from both sides. So, Y 1 hat is equal to P Y 1. Then we replace Y 1 by Y 1 hat in equation 1. So, in this equation we replace Y 1 by Y 1 hat. So, you get small y 1 equal to y 1 hat beta plus x 1 gamma plus u 1 minus v 1 beta, where y 1 minus y 1 hat is equal to v 1. Now, we apply OLS to this equation. So, basically what we have done, at the first stage we have obtained the predicted value of y, and then from there we can get the predicted value of y 1, say y 1 hat, and then in the model we replace y 1 by y 1 hat. So, you have this relation. Now, in this relation we estimate beta and gamma by applying the OLS procedure. So, at the second stage we apply OLS procedure to this equation, and then we get the two-stage least square estimator as, say, we denote it by B c equal to, we can write y 1 equal to, say, y 1 hat x 1 beta gamma plus, say, you write it u 1 star. U 1 star is equal to u 1 minus v 1 beta. So, how we get the OLS estimators for beta gamma? So, for simple model y equal to x beta plus u, the expression for OLS estimator is x transpose x inverse x transpose y. So, we apply this formula. We take transpose of this. So, we get y 1 hat transpose x 1 transpose, then y 1 hat x 1, and then we multiply these two. So, you get y 1 hat transpose y 1 hat here, then y 1 hat transpose x 1, x 1 transpose y 1 hat, x 1 transpose x 1, then we take inverse of this, and then you have x transpose y. So, you replace x transpose by y 1 hat transpose x 1 transpose and y by y 1. So, you get y 1 hat transpose y 1 x 1 transpose y 1, or B c is equal to, we substitute the value of y 1 hat, y 1 hat is equal to P y 1. So, y 1 hat transpose y 1 hat, P is a symmetric idempotent matrix. So, this is equal to y 1 transpose P y 1, and P is equal to x transpose x inverse x transpose. So, you get this expression. Then you have y 1 hat transpose x 1. Y 1 hat transpose x 1 is actually equal to y 1 transpose x 1, because y 1 hat is equal to x transpose x inverse x transpose, and then if you take x transpose y 1 hat, then you also have y 1 here. If you take x transpose x inverse x transpose, then this is equal to x transpose. Or if you take x 1 transpose x transpose x inverse x transpose, then this is equal to x 1 transpose. You simply write capital X in terms of x 1 and x 2. So, you get this relation. Or if you take x 1 transpose x transpose x inverse x transpose x 1, then what you get? Here you obtain x 1 transpose x 1. You combine these terms, you get x 1 transpose and then you get x 1 here. So, if you take this term x transpose y 1 hat, then x transpose y 1 hat is equal to x transpose x transpose x inverse x transpose y 1. So, this is equal to x transpose y 1. So, y 1 hat transpose x 1 is equal to y 1 transpose x 1, and then this term is equal to x 1 transpose x transpose x inverse x transpose y 1, and then further you can solve it using this relation. And here you have x 1 transpose x 1. Then y 1 hat transpose small y 1, you just substitute the value of y 1 hat here, you get this expression, and then you have x 1 transpose y 1 here. So, further we solve this equation. So, this is equal to x 1 transpose y 1. So, you get B C equal to this expression. Further, we can write this equation 1 as, say, y 1 equal to z 1 delta plus u 1, where z 1 is y 1 x 1. We write z 1 equal to y 1 x 1 and delta equal to beta gamma. Then the two stage least square estimator for delta is, say, we denoted by d 2 SLS, which is equal to B C. Now, this is equal to z 1 transpose x transpose x inverse x transpose z 1 whole inverse z 1 transpose x transpose x inverse x transpose y 1. Now, one can easily verify it. If you substitute the value of z 1 here, then what you get? Here you obtain y 1 transpose x transpose x inverse x transpose y 1, and then you have y 1 transpose x capital Y 1 transpose x transpose x inverse x transpose x 1, which is equal to y 1 transpose x 1. Similarly, at this place you get x 1 transpose y 1, and here you get x 1 transpose x 1. Notice that to obtain this expression, you just make use of the result that x 1 transpose x transpose x inverse x transpose x 1 is equal to x 1 transpose x 1. And so, this is the expression for 2 SLS estimator for delta or beta gamma. Now, we consider the interpretation of 2SLS estimator as an instrumental variable estimator. Now, suppose W is any matrix of instrumental variables. Then we define the instrumental variable estimator of delta as DIV equal to W transpose Z1 inverse W transpose Y1. Actually, you have this model or this model. So, we just pre-multiply it by W transpose and then we get this instrumental variable estimator. Now, suppose you set W equal to Y1 hat x1, where Y1 hat is equal to x transpose x inverse x transpose Y1, that is the predicted value of Y1. Then W transpose Z1 is equal to, get W transpose equal to Y1 hat transpose x1 transpose, then Z1 is Y1 x1 and then you simplify it, you just substitute the value of Y1 hat here and then you get Z1 transpose x, x transpose x inverse x transpose Z1 here, this expression. So, W transpose Z1 is this. Then W transpose Y1 is equal to, again you have Y1 hat transpose Y1 and x1 transpose Y1. Then we substitute the value of Y1 hat here and then we also make use of this result. And finally, you obtain this expression. And then for W equal to Y1 hat x1, you can easily verify that the instrumental variable estimator is your 2-stage least square estimator, because just replace W transpose Z1 by this expression and W transpose small y1 by this expression. You get this expression for the 2-stage least square estimator. So, for this particular choice of capital W, the matrix of instrumental variables, you get the 2-stage least square estimator. Then we prove the consistency of 2-stage least square estimator. Now, suppose as n tends to infinity, the probability limit of n inverse y1 transpose x is sigma y1 x. This is a finite matrix. Then the probability limit of n inverse x transpose x is sigma x x. This is also a finite matrix. And probability limit of n inverse x transpose u1 is equal to 0. Then 2-stage least square estimator is a consistent estimator. To prove this result, say suppose you write W equal to say Z1 hat equal to x transpose x inverse x transpose y1. Actually, this is equal to y1 hat, this part, and x1. So, W is equal to y1 hat x1, and then we write it equal to P Z1, where P is equal to x transpose x inverse x transpose. So, P is an idempotent symmetric matrix. Further, Z1 hat transpose Z1 hat is equal to Z1 transpose P Z1 and this is equal to Z1 hat transpose Z1. Then the 2-stage least square estimator is say Z1 hat transpose Z1 hat whole inverse Z1 hat transpose Y1, because actually Z1 hat transpose Z1 hat is equal to Z1 transpose P Z1, which is equal to Z1 transpose x, x transpose x inverse x transpose Z1. And similarly, you can write this expression. So, finally, this is the two stage least square estimator, and then we write y 1 equal to z 1 delta plus u 1. So, when we write y 1 equal to z 1 delta, then we get say z 1 hat transpose z 1 hat inverse, then you have z 1 hat transpose z 1 delta plus z 1 hat transpose z 1 hat inverse z 1 hat transpose u 1. Now, we make use of this result. So, here you get identity matrix. So, this is equal to delta plus this expression. So, d 2 SLS minus delta is equal to z 1 hat transpose z 1 hat inverse z 1 hat transpose u 1, and then we take the probability limit. So, we divide this expression by n, and then you have inverse here. So, you again divide this expression by n. Now, probability limit of 1 upon n z 1 transpose x is equal to say sigma y 1 x sigma x 1 x. Just write z 1 equal to y 1 x 1. So, you get this expression, and we write this equal to sigma z 1 x say. Then probability limit of 1 upon n z 1 hat transpose z 1 hat is equal to probability limit of 1 upon n. We substitute the value of z 1 hat here. So, you get z 1 transpose x, then probability limit of 1 upon n x transpose x inverse, then probability limit of 1 upon n x transpose z 1, and we write this expression equal to sigma z 1 x, then sigma x x inverse, then sigma x z 1, and probability limit of 1 upon n z 1 hat transpose u 1 is equal to 0. So, probability limit of 2 SLS minus delta is equal to 0, because you have a term involving 1 upon n z 1 hat transpose u 1, and this has probability limit 0. Further, if you obtain the asymptotic variance covariance matrix of D 2 SLS minus delta, you simply take D 2 SLS minus delta, and then you take transpose of this, and then you take probability limit of this. So, finally, you obtain sigma 1 1 upon n sigma z 1 x sigma x x inverse sigma x z 1 whole inverse. So, if you take limit n tending to infinity, this asymptotic variance covariance matrix tends to 0 because of this term. So, if you combine these two results, means the probability limit of D 2 SLS minus delta is equal to 0, and its variance covariance asymptotic variance covariance matrix actually tends to 0 as n tends to infinity. So, this shows that D 2 SLS is a consistent estimator of delta. Further, you can obtain a consistent estimator of this asymptotic variance covariance matrix. Say we estimate sigma 1 1 by S 1 1, then you have 1 upon probability limit of 1 upon n sigma z 1 x, and then you estimate sigma z 1 x by 1 upon n z 1 transpose x. You estimate sigma x x inverse or sigma x x by 1 upon n x transpose x. and so on. So, finally, you get this estimator for the asymptotic variance covariance matrix, where S11 is equal to 1 upon n y 1 minus capital Y 1 b minus x 1 c transpose, and then you have this expression. So, this is a consistent estimator of sigma 1 1. Now, in case of exactly identified equation, capital K minus small k is equal to m minus 1. Then in that case, if you look at this matrix Z 1 transpose x, this is a square matrix. And then you can write this inverse as, say, inverse of x transpose Z 1, then inverse of x transpose x inverse, which is x transpose x, and then you have Z 1 transpose x whole inverse. And then you have Z 1 transpose x, x transpose x inverse, x transpose. So, finally, you obtain, say, here you get identity matrix, then if you combine this with this, you get identity matrix and so on. So, you get x transpose Z 1 inverse x transpose. So, in this case, the expression for two stage least square estimator reduces to x transpose Z 1 inverse x transpose Y 1. So, in this particular case, the 2 SRS estimator coincides with ILS estimator. So, in case of just identified equation, the two estimators are identical. Here notice that Z 1 is equal to Y 1 x 1, and Y 1 has m minus 1 columns and x 1 has small k columns. Further, x has capital K columns. Now, if you look at x transpose Z 1, the order of x transpose Z 1 is k cross m plus k minus 1. Now, in case of exact identification, means when capital K minus small k is equal to m minus 1, then you have capital K equal to m plus k minus 1. So, this matrix is a square matrix. Similarly, in this case, Z 1 transpose x is also a square matrix. So, in case of exact identification, you get square matrices here, and then you can apply this result. And then you get the same expression for indirect least square estimator and two stage least square estimator. Now, we consider this example of demand function and supply function. Here Q and P are endogenous variables, capital M is equal to 2, 1, I, R and P t minus 1, these are the predetermined variables. So, capital K is equal to 4. You can easily verify that the demand function is just identified and the supply function is over identified. Then, for obtaining the 2 SRS estimator, what we do? We first run OLS for, say, P t equal to pi naught plus pi 1 I t plus pi 2 R t plus pi 3 P t minus 1 plus V t. So, we run regression between P t and all the endogenous variables or predetermined variables. We take all the predetermined variables here, and then we obtain the OLS estimators for all the pi's, and then we get the predicted value of P t from here. Then for estimating the demand function, we run OLS for this, means in the demand function we replace P t by its predicted value, and then we run regression. And if we run regression, we simply you run OLS here, you get the two SRS estimators for alpha naught, alpha 1 and alpha 2, of course, alpha 3 also. Further, for estimating the supply function, in the supply function we replace P t by its predicted value, and then we run regression, simple OLS, and we estimate beta naught, beta 1, beta 2. So, in over identified equations, the indirect least squares provides multiple estimates of parameters, whereas 2 SRS provides only one estimate per parameter. So, you get unique estimators. In two-stage least square, you require total number of predetermined variables in the system. When you apply indirect least squares, you just require those predetermined variables which are included in the system, in that particular equation, not all the predetermined variables included in the system, but in 2 SRS you require all the predetermined variables in the system. This method can also be applied to exactly identified case, and this method provides a consistent estimator. Now, we come to the limited information maximum likelihood estimators. Say, suppose you write the ith equation as, say, small y I equal to capital Y beta I plus x I gamma I plus u I equal to 1 to capital M, or we write it as y I equal to z I delta I plus u I, where z I is of order n cross m I plus k I minus 1. So, in fact, z I is equal to capital Y I x I, and then delta I is equal to beta I gamma I. Limited information maximum likelihood estimator is obtained by maximizing the likelihood function derived from the stochastic elements of this single equation 3. Now, what are the stochastic elements of this equation or this equation? You have small y I here and capital Y I. So, these are the stochastic elements. So, while calculating the likelihood function, you have to consider these two variables. You must keep these two variables in mind, small y I and capital Y I. Now, here capital B I is equal to minus 1 beta I 0. This beta I has small m I minus 1 parameters involved in it. Further, capital gamma I is equal to small gamma I 0, and this gamma I has k I parameters, and therefore, the total number of parameters is small m I minus 1 plus k I. So, these total number of unknown elements is this. These zeros are corresponding to the endogenous variables not included in the ith equation, and these zeros are corresponding to the predetermined variables not included in the ith equation. So, the variables which are not included in the ith equation, the coefficients corresponding to those variables are taken as 0. Now, we can write the capital M equations of 2 jointly as, say, y equal to z delta plus u. So, we combine all the m equations where small y is equal to say y 1, y 2, so on y capital M, and capital Z is equal to say corresponding to the first equation you have Z 1 here, then 0 0, so on 0, then you have 0 Z 2, so on 0, and so on 0 0 and so on Z m. Delta is equal to delta 1, delta 2, delta capital M, and u is equal to u 1, u 2, u capital M. So, if you multiply Z delta, then say the first equation is y 1 equal to, you get Z 1 delta 1 plus 0 delta 2, so on plus 0 delta m. So, you get Z 1 delta 1 plus u 1. Then y 2 is equal to Z 2 delta 2 plus u 2 and so on. Y m is equal to Z m delta m plus u m. So, you can combine all the capital M equations in this form. Here capital Z is of order n capital M cross summation I equal to 1 to capital M m I minus 1 plus k I. Say corresponding to the ith equation, Z I has m I minus 1 plus k I columns. So, total number of columns in Z matrix is summation I equal to 1 to m I minus 1 plus k I. And then delta is of order summation I equal to 1 to m I minus 1 plus k I cross 1. And small y and u are of orders n into capital M cross 1. Now, we write the likelihood function. So, under the assumption of normality of disturbances, the likelihood function is say L delta star sigma star given y star equal to, here actually y star is equal to vector small y I capital Y I, means you consider small y I and capital Y I, and you write all the elements in the form of a vector. Now, how many variables are there? 1 and m I minus 1. So, in all you have m I, and each of these vectors is of order n, means each vector has n rows. This vector has n rows, means this vector has n elements, and this matrix capital Y I has n rows. So, in all you get n into m I elements in this vector y star. Then Z star is sub matrix of capital Z involving Z 1, Z 2, Z m I, and sigma star is m I cross m I sub matrix sigma related to structural errors of y star. And again notice that your likelihood function corresponding to ith equation is just based on these variables, these m I variables. So, you consider the variance covariance matrix or the sub matrix of capital sigma related to structural errors of y star only. And then you have the likelihood function 2 pi to the power minus n m by 2 determinant value of sigma star canonical product I n to the power minus 1 upon 2. Then you have determinants capital gamma star to the power n exponential minus half y star minus z star delta star transpose sigma star canonical product I n inverse y star minus z star delta star. So, you have this likelihood function. Then we maximize this likelihood function subject to identification restrictions of the ith equation, and then we get the limited information maximum likelihood estimator. The limited information maximum likelihood estimator is efficient among the single equation estimators under the assumption of normality of disturbances. We are taking the assumption of normality of disturbances, and under this assumption this limited information maximum likelihood estimator is efficient among the single equation estimators. Notice that here you are considering the likelihood function for a single equation, say small y I, capital Y I, x I. So, your likelihood function is based on small y I and capital Y I. Here in this lecture we have not derived the expression for the limited information maximum likelihood estimator, but in next lecture I will discuss the Pagan's procedure for obtaining the expression for the limited information maximum likelihood estimator. Further, so far we have discussed indirect least square procedure, two-stage least square procedure, or limited information maximum likelihood estimator. All these estimators are limited information estimators in the sense that when deriving these estimators, we have used the information contained in a particular structural equations. So, suppose you are interested in estimating the parameters of a particular structural equation, say ith equation. Then your estimator utilizes or it makes use of the information contained in that particular ith equation. So, in this sense these estimators are called limited information estimators. Now, sometimes your different equations may have some kind of correlation also. So, disturbances of different equations are correlated with each other. It means the information about the parameters of a particular equation is also contained in other equations. In limited information estimators, we do not utilize such kind of information. For that purpose, we require full information estimators, the estimators which are based on the entire system of equations. So, in the next lecture, I will discuss the Pagan's procedure for obtaining the limited information maximum likelihood estimator, and then we will discuss the three-stage least square estimator, which is the full information estimator, and full information maximum likelihood estimator for estimating the parameters. So, I am going to stop here. Thank you.